There we go. Okay, yeah. So part one of the assignment, you're just doing some basic math stuff, just some questions, whatever. And then part two is you're building some logic with some circuitry in digital. Okay? For part two, there is this you download, and it tells you down here, like use this file, and then you make your changes in that file. It's got tests built in, so you'll know if you're right or wrong. Just because the test passed doesn't mean you're going to get perfect. You may have cheesed it, which in that case you won't get perfect. But I don't think it's too bad. Some of these questions, like most of these questions I find are more like puzzles than anything else, right? So just take your time with it, try to have some fun. So there's some hints on this submitting. For part one, you must submit a PDF. Text file? No. Word file? No. PDF? Yes. If your question is, can it be not a PDF? The answer is no. It must be a PDF.
No, on the question with adding binary numbers, how do you want us to show carrying the ones if we need to have it typed up?
Okay, I understand what you mean. Yeah, you're right, because there's no easy way. Do your best.
To figure out how to do
We're using LaTeX?
I'm using LaTeX. Yeah.
You're using LaTeX? If you can't...
I managed to make it so show you doing the vertical addition, and I have little ones on top.
Perfect. Do your best. Do your best. He's right. Do your best on showing the carrying of the ones in the addition in your math formatting. Because yeah, you're right. Now that I think of it, it's not easy to do what do you call that, long addition? I don't know, when you just kind of stack them vertically and you carry. Just do your best, okay? If I can look at your answer and be like, yeah, they did something. If I look at your answer and be like, they didn't try anything, that's what I mean. For those of you, raise your hand if you're familiar with LaTeX or LaTeX or LaTeX or LaTeX or whatever you want to call it. If you, by all means, use that. I encourage you to use that. Submit the PDF. Do not submit the text file. I'm not going to build your crap. If you don't know what that is, that's entirely fine. You can use Microsoft Word, but when you're done, again, do not submit the Word file. Do not do that. Submit a PDF. How do you convert it to a PDF? Well, in Save As, I believe there's a PDF option somewhere. PDF. Is there a PDF in here? Where is it? Ah, there you go. See? Save it as a PDF. If you don't like that option, you can also usually print to a PDF. Somewhere in here, settings. But anyways, point being, if it's not a PDF, it ain't getting marked, okay? You'll get 0 on that part of the assignment. No ifs, ands, or buts. You've been warned. Also, if you're like, well, how do I use fancy math syntax? Well, if you're using LaTeX, I assume you know, okay? If you're using Microsoft Word, you can go, I haven't done this in a while, and they've changed the layout of Word, so I'm not 100% sure, but I think it's insert equation. Yes, perfect. And now you've got all of these fancy options, right? So if you're like, well, I've got 101. Oh my gosh, look at that. You can even do, wow. Look at that, 101. I'm going to use that one. 101. Oh, look at that. Wow. So that's the number 101, right? No. What number is that? 5, obviously. Why? Because it's base 2. Why? Because there's a little subscript there for base 2. Make it proper syntax. If it's not, you ain't getting your marks. If this is too hard for you, reevaluate your decisions in life. Okay? You can figure this one out. Any last questions about that? Yeah?
I will take it on paper and then scan it as PDF.
Right? No. No, you may not. Nice try, though. Good question, but no, you can't. I get it. I know, I get it, but no. Because otherwise, you end up with the answer is no. Good question, though, but no. I do say that in the assignment because, yeah. Other questions? To clarify, if anyone didn't hear, his question was, can I write it on paper and then scan it and submit it as a PDF? No, we're not going to do that. If you've got some wild system where you can scan it and then you have software that can do optical character recognition and then convert it to something, and it's this nice typeset PDF, by all means, go ahead. But it's probably just easier to type it. Yeah. All right. So back to logic gates. So blitzing review, we covered these 3 gates, right? Did we cover all 3? I'm pretty sure we did, right? Not. Remember, the idea is there's a plug here, water flows, and it backs up and goes out, turns that on, right? We turn on that switch, we hit the plug, the plug's gone, the water goes straight down. It gets sunk to 0. If you can kind of think of it as this resistor is kind of like slowing down the water flow such that the rate in which it drains is way faster than the rate in which it can fill up. If we go here with OR, either of them needs to be on. Both of these valves are off. As soon as one opens, it can flow. Again, the resistor is kind of like it slows the flow. So yeah, whatever's in here will drain. But if one of these opens up, the rate in which it can fill up is faster than it can drain. That's how we can think of it. That's not how it really works, but that's how we think of it. We can think of it. It goes down, it fills and goes. If both valves are open, it works just fine. And then finally with AND, same idea, but both need to be on. All right? Now, one thing you might notice it might be hard to tell, but that's a different color, by the way. This means there's a charge on it, okay? This means there is, now, technically no charge is like a charge, right? So this is like, it's connected to a voltage source. It's dark green, it's connected to ground. But this thing in the middle is connected to neither. So it might sound like, okay, on, off, what else is there? Kind of like this weird, neither. And this is going to come up a little bit more as we go. Not too important, just be aware that oh yeah, there's this weird, kind of like third state there. Yeah? If I ask you, what's that voltage? You don't know, by the way. Any questions about any of these 3 things we're seeing right here? These 3 gates. With these 3 transistor configurations, which, again, by the way, I said this last time, just to restate it. If you look through your textbook, did anyone in here get the textbook? Okay, well, if you were to look into that textbook, you would see that these are not the configurations they have. They've kind of over-designed it to address physical limitations that we have in the real world that we don't care about in digital, which is fine because we're talking about this from not so much of an engineering perspective where those things are important, but more from a pure computational mathematical side of things where this is how we can implement them with these real world ideas, but we're not worried about those real physical constraints. Okay? So basically they have on-off switch. So when it's on, there would be a switch on here, but off here, and then when you flip it, it's a whole thing. They engineered it to work more safely, but again, we don't care about those situations. With these 3 transistor designs, and there are other designs we can have for these things, because remember, there's an infinite number of ways to solve any problem, but some are better than others. With these designs, we can generate anything. With these designs, we can build a whole computer. Okay? We can achieve not and or different ways, like I was saying, but here's some straightforward ways to generate these 3 things, these 3 very important Boolean operations. And if we go back, we can see, if we go back, 2 topics, where we were talking about Boolean algebra, we have got those 2 states, those 2 values, on or off, true, false, and those 3 operators we really cared about, and or not. We're all set. We've got everything we need. Okay. The symbol for AND. Did I show you the symbol for? Yeah, okay, there's a symbol for and, the symbol for or, and the symbol for not is this like little triangle thing. Now, really, it's the circle that's important. The triangle is, it's something slightly different. It doesn't matter too much. But the circle's really what we care about. The triangle means like a buffer component, but this is usually how we would draw like a NOT gate, okay? It's actually common to simplify a NOT. If we have look, at this particular design right here, we've got an input and another input and an output. Now, in what conditions, like think of this as a truth table. In fact, let's do this really quick, just as a good exercise. Let's call this like A, B, and O, all right? Zero, 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 one, one, zero, one, one. If both are off, if both are zero, will the output be high? Zero. Zero. That's correct for multiple reasons, yes. Now, we have A, B. 0, 1. Will the output be high? Yeah. Why? Because if this is 0, well, what's not 0? 1. And what's 1? 1. So 1 and 1, 1. If you don't like this, we could also do, well, what's not A? Okay, 1, 1, 0, 0. So we can see B and not A when they're both, right? And then 0, 0 becomes a little more obvious when you do it that way, when we include all the steps. So this configuration there, that's like how we could draw a truth table for that. We can also go the other way where I give you a truth table and say, build a circuit that does this. But anyways, because it's common to have like, you want to invert an input right before you put it into the some gate, it's common to draw it like that. Now, when I'm drawing my designs, depending on the design, I may or may not do that, but this is a common thing to see. This means, okay, not A and B. We're inverting the input right before going into the gate, just as like a shorthand. Cool? Cool. Other gate symbols. Well, here's not or. If you're confused, well, it's just an OR gate with a not, the circle in front. You can think of it as an OR gate where the, well, oh, and the circle means invert the output. Oh, what's not or? Not or is not or. Shockingly, here's a not and or NAND. Okay, why? Well, it's an AND gate with a little circle out front. Here's another one, exclusive OR. This, I know, right? Yeah. Want to take a wild guess what like not exclusive OR would be? Nailed it. Look at that. Genius right there, everybody. Do I have it there? I don't. Oh my gosh, I don't even show it. Okay. Well, anyways, not exclusive OR. That's the symbol, exclusive OR. Do you remember what exclusive OR is?
Only one of them is true.
Oh, yeah. Otherwise false, yeah. Exclusive OR, that's either of the inputs are true, but not both of the inputs are true. It would be like, am I wearing shoes, exclusive OR a shirt? No, because I've got both, right? Questions, thoughts, concerns, comments, anything about this so far? All right. All right, additional inputs. So these logic gates usually, traditionally, have 2 inputs. But it's common to want to have several inputs, okay? So here's an example and with 5 inputs. Now, if we think about, okay, what does this mean? This really is shorthand for a series of AND gates put together. And, where's the eraser? There it is. I guess I'll draw it over here. And like, no, I don't want that. Right there. There's 5 input ands. Okay? Now you may be wondering, well, could we have done something like this? What's the answer to that? Could it be that?
Sure.
Yeah. It doesn't matter. Because the order in which we do ands doesn't matter. If they're all ands, it's entirely fine. In the same way that if I say 1 plus 2 plus 3, does it matter that I do 1 plus 2 first? Or 2 plus 3 first? No, it doesn't. Okay? Or 1 plus 3. It doesn't matter. The order doesn't matter. It really doesn't. The order in which I combine these inputs doesn't matter at all. Exactly. In fact, we can go and review. And when you really think about it, here, let's go back here. There it is. The order of ands and ors doesn't matter. All right? So not only like does this show us that the order doesn't matter, but because the order doesn't matter, we could just kind of like A and B and C, because the order doesn't matter, we can just say, like, let's just draw an AND gate with 3 inputs and know that it means ANDs them all together. Similarly with ORs. It ORs them all together. Okay? And, like, remember when we were talking about these principles here? Like, these principles are like a first layer of abstraction above, like, the basic things of the end of the true, false, and or nots. These properties are like basic observations we can make about those core like axioms. These like, okay, this is what we're starting with. The ands, ors, and nots, and true or false. Remember how I was saying that? This is like the first layer of like, oh, if we apply these things, and like we can observe that with these 5 things, the 2 values and the 3 operators, we can observe that, oh, associativity it holds. Well, we know that. And because we know that, we can jump to this, right? That's the point I'm making here. Because of the associativity rule, which is not a baseline starting position, but it's one of the first conclusions we can make, one of our first like theorems, for lack of a better term, we can make from what we're starting with. Because of that, and it's obvious, we can jump straight to this. And we can pretend this is like one of our basic building blocks. Even though this is not a statement that we start with, meaning a true or false or an and or a not, but because of what we can observe, those basic algebraic properties, we can go to this. Is that clear? Is my point clear? We didn't start with this, but we can easily get to this and know that this is like safe enough to throw on the page. This is a 4-input OR. You can have as many as you want. Here's a 4-input NAND. Okay? NAND with more than 2 inputs is an AND gate with the same number of inputs but an inverted output. Yeah. In other words, output's 1 as long as not all the inputs are 1. At least 1 is 0. A NOR gate with more than 2 inputs is the same as an OR gate with the same number of inputs, just with an inverted output. Now, XOR is actually kind of a little, it's kind of funny. Because if you're, like, you might think like, okay, wait, what would XOR be? Like not and is obvious, but what would exclusive OR be with 3 inputs? What should it be? Right? Think about that for a second. It's kind of a funny one. Well, it turns out that exclusive OR, the way we got it operating is it works. Here, let's maybe we can draw it out. A, B, and C. All right, you ready? Okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, do I have them all? 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. So let's think. Okay, let's start with like A, B. Okay? So, okay, 0, 0, 1, 1, 1, 1, 0, 0. Okay. Then, like, okay, well, let's say like A, B, C, right? So now I want to do these two. Okay, so 0, 1, 1, 0, 1, 0, 0, 1. So like what do we see there? Can we, like, what is it doing? First, do we agree that did I do this right? I may not have. I'm asking, like, that was a serious question. Did I do it right? All I did was A XOR B, these two columns I looked at, I ignored C, and then I took the result of A XOR B with C to generate this column by basically, okay, I did exclusive OR on these two columns. 0, 1's 1, 1's 1, both false. 1, 0, 0, 1. What observation can we make?
1 is an odd number of 1s.
Yeah. It's more of like, sometimes we call this like a parity check or something. With more than 2 inputs, it effectively works as a parity check. Check if the number of 1 inputs is even or odd. Output 0 when there's an even number of 1s, output 1 when there's an odd number of 1s. And we could do this as we go on and on and on and on and on. It's basically, if it's even, 0. If it's odd, 1. Cool? Cool. What would it be? So is not XOR the same as like exclusive OR on NORs? Like, right? Like, is not XOR the same as exclusive OR on NORs? We'll think about that one. Maybe we'll do that in lab tomorrow or something. Is my question clear? Like, that was XOR, and if I not the output, what happens if I do like exclusive OR on NORs? Like, is that the same as not XOR? That's my question. Well, probably have to think about that one. Any questions, thoughts, concerns, comments before we carry on? All right. All right, combinational logic. I think if you type this into a word processor, it's going to be like, did you mean combinatorial? No, we don't. We mean combinational. With these logic gates, which we can already see that, let's take a moment and appreciate where we are. On the math side of things, from strictly the algebra, we started with and, or, not, and true, false. We saw some of those algebraic properties, which are a layer of abstraction up, right? On the like physical, simulated physical side, we were able to build like switches with transistors and then the logic gates with transistors, meaning we could implement and, or, and not in circuitry. And we were already able to kind of like configure these things that like were in practice those Boolean algebraic properties, right? So, you know, these things exist in like parallel alongside each other, and we're building from these things, okay? So we're about to start jumping to another layer of abstraction here. With an understanding of logic gates, more complex logical structures can be constructed. Here, we're going to make some structures that can make decisions, you know, for lack of a better term, based on some combination of inputs. We will structures that can make decisions based on some combination of inputs will be explored. Yeah, okay, that's what I meant to say. Decoders. So consider a situation where an input signal, we have an input signal. I want that input signal to control two outputs. Basically, actually, which output is being used. When the input signal is low, one of the two outputs is high. When the input signal is high, the other output should be high. What I mean is something that looks like this. So, when we were using logic gates, we were kind of coming from it with the case of like I have two inputs and one output. Now we're kind of going the other way, where when the input, like we have like one input, but two outputs. One input controls two outputs, so we flipped it. Until now, all the truth tables, as a note, all the truth tables were shown to demonstrate how Boolean operations worked, each taking some number of inputs and producing a single output. These truth tables were used to describe how each operator worked. Here, a truth table is not describing any specific operator, but some desired functionality. So if we look at this, right, like this was like, okay, here's A, B, here's not A, and here's some output I wanted, right? This is more along the lines of like, this is what I want to happen, but I don't know what operation it is. This is just my output. That's kind of what I'm showing here. Like, what's the operation to do this? I don't know, but this is what I want. So I'm using the truth table kind of from like the flip side. I'm not describing an operator. I'm not describing the functionality of an operator. I'm describing the functionality in looking for the operator, kind of, or operations that I need. Okay, here the truth table is not describing any specific operator, but some desired functionality. The goal would then be to construct some circuit with logic gates and inputs and outputs to produce the desired functionality. Further, it's showing how to describe functionality, how the desired functionality, has more than one input. Oh, my goodness, output. I'm full. I don't know what's going on. I need more coffee. More specifically, when the input is 0, output A should be 0, output B should be 1. And when the input is 1, output A should be 1, and output B should be 0. Okay? That's the state of things. So the state of the input affects both outputs. Yeah, I guess you could kind of think of it, well, it's only really affecting the one. Well, it's kind of affecting both. We'll see. Also, you may have noticed, I was just talking, the state of the input, the state. Obviously, these computational systems and all the code we've ever written before, states. Raise your hand if you've had me before for like 101 and 102, 161 and 162. Okay, so you know that I have a really big emphasis on avoiding stateful code. We want everything to be immutable. Of course, everything has a state, but we don't want that state to change, right? Now, so at this high-level programming that we do, like in Java or Python or whatever, it's nice to avoid mutability. We like immutable things. We like to avoid statefulness. When you get down to this level, surprise, everything's stateful. It just is, okay? It's how our computers work. Deal with it. So if you're like, hey, I remember him always going on about statefulness. There's no getting around it here, okay? So based on the truth table, how could this functionality be achieved with Boolean operators? Output A is the inversion of the input, and output B is simply the input. Well, okay, so take a moment, look at that. Think for a second. If we had digital open and we have those logic gates, not and nor, inputs, outputs, how could I control this? Well, we could do something as simple as this. We've got some input. This is what I would call a 1-bit decoder. And you could almost think of this as like output 0 and output 1. When the bit is 0, output 0 is high. When the bit is 1, output 1 is high. We could think of it like that if we wanted. But do we see? There we go. This is perhaps, like it's kind of weird to look, okay, 2 outputs, okay, but there's nothing wrong with that. And we could have 1 input split to go into 2 outputs. There's nothing wrong with what we're looking at here. This is all safe, nothing weird going on. So that's our 1-bit decoder. No matter what, one of those 2 outputs is high though, right? Any questions about this? Do you not have any questions because it's scary, or is it because it's so obvious? Neither, apparently. Cool? This one may, be honest if you're like, I guess, like be honest if you're like, I wouldn't have thought of that, but obviously. Are you all quiet because you thought of this? You thought of it? Okay, good. Wonderful. I guess this is, you guys are way smarter than I thought. This is wonderful. All right, so things are about to get wild though, so don't worry. All right, more than 1 input bit. Okay, so, okay, let me finish this point here. This is an example of a single bit decoder. The 1 input signal can be thought of as a single bit. The input signal is decoded to control the output signals. More than 1 input bit. So, okay, now consider a situation where 4 separate circuits need to be controlled by a controller. Like here, I've got 2 outputs. Maybe this output is like, who knows what this could be controlling, but maybe like I've got like a toggle switch basically, right? I'm now watering garden bed A, and now I press the button, I'm now watering garden bed B. Okay? And I'm in my house looking down at my garden bed getting water. I'm like, this is wonderful, right? I don't need to go down there and do anything. I've got this button to control. But then suddenly, you decide you want 4 garden beds, or 8 garden beds, or something else, right? But let's say 4. I've got 4 garden beds, and I want to have a button to control which one is being watered. Okay, up in my bedroom. I'm too lazy to go down and water them myself, so I need a button to do it. Well, unfortunately, I can't do it with a single button, because a single button can only have 2 states, 0 or 1. I would need 2 buttons to control 4 different things, right? Why? Well, think of the 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 combinations. So, because I can have 4 unique states, I can have it control 4 unique things. But how do I design this? Oh, yeah. Okay, so there needs to be a way to specify which of the 4 circuits should be running at any given time. But unfortunately, a single bit of information can only decode 2 states. 2 inputs can have 4 unique states, continuing the idea that signals can be thought of as single bits. 2 signals can be thought of as 2-bit binary number. Each of these corresponds to the 0 to 3 circuits, right? Do we see what I mean when I say like, okay, these 2 buttons can have 4 states, but we can assign these 4 states numbers, and in fact, why don't we assign them the numbers that correspond to the binary, like the base 2 number, right? 0, 0, well that's 0, 0, 1, that's 1, 1, 0, that's 2, 1, 1, that's 3. My point here is the numbering of these 4 states is not arbitrary. It's designed to match the binary, like the base 2 number. Cool? So great, now I also have like a nice way to label these things. So the truth table below describes this functionality. 0, 0, I want this output. 0, 1, I want output 1. 1, 0, output 2, 1, 1, output 3. Again, notice that that's the binary number 0, output 0. Binary number 1, output 1. Binary number 2, output 2. Binary number 3, output 3. Right? Cool. So, how do we design a circuit for this? Think about, first of all, I find it really helps to think of these like as 4 separate circuits kind of stuck together. Although in this particular case, that might not be that helpful. How do you design it? Think for a moment. Consider the first row. This is a big hint. Consider the first row in output 0. When input A is not high and input B is not high, output high only for input 1. So how do I achieve this? Well, this functionality can be achieved with a single 2 input AND gates with both inputs inverted, right? Like 0 invert is 1, 0 invert is 1, and that together we get that. In fact, that would actually work for all of input 0. So, Oh, yeah. So that's AND gate. This will work only for output 1 when both inputs are output 1. This AND will only output 1. Oh, okay, yeah. When I got confused because I thought I was talking about output 1, not output the signal 1. I was confused. In fact, I'm wondering if I should reword that to be like high or something. Yeah. Now consider row 2. Okay, I'm not going to say any more, and I don't want to spoil it, but I'm going to give you a moment. I'm going to give you a minute. Think. Start to think. If you have scrap paper, maybe like drawing something might help here. But how could you, how could you build this? Like, what would you do? How could you build it? And take a moment to truly think about it, because if you don't spend your time thinking about this, this will never click for you. You have to actually try to engage with this content. So take a moment and think. How could you do that? If you're drawing it out, you'll probably quickly discover the pattern. Does that work well on a tablet? Is that digital? Oh no, you're just drawing. I thought it was, and I was like, does it work on tablet? Oh.
Get it on surface focus.
Probably, yeah. So, first, let's make sure it makes sense that this actually works. I know I said first row, but this actually works for all rows, all input combinations, and output 0. If A and B are 0, they both get inverted to be a 1, and then 1 and 1, output high. 0, 1 becomes 1, 0. That's not how AND works. 1, 0 becomes 0, 1, output 0 because that's AND. And then, of course, 1, 1 becomes 0, 0, 0, and 0 is 0. So this right here perfectly corresponds to output 1. But, sorry, output 0, pardon me. Now output 1. Well, I want it to be not A and B. Gives me output 1. So that would be not A and then B. Output 1. And we can just kind of draw like A, B like that. And it might start to feel, what did I do something wrong? Oh, they did. There we go. Much better. In fact, it might even feel kind of like we're cheesing this a bit, eh? Like, well, okay, you're just kind of like, let me guess, the next one is this? Yep. And how about this? No ands. Yeah, nailed it. That's the pattern. We're like, it almost feels like we're hard coding the inputs to our ands, and that's like exactly what we're doing. This pattern generalizes really well. In fact, if we go back to here, you might be like, well, there's no AND gate. Well, correct, but it's like the same pattern, but you know, it'd be like ANDing something with itself, which is itself, so it doesn't really matter. This pattern would work for 3 inputs, 4 inputs, 5 inputs, 6 inputs. Cool? Does this make sense? This is what we call a decoder. Now consider row 1 and output 1. A is not high and B is high. Well, that's just that, right? And if we carry on, there we go. This is a decoder. We've got these 2 signals. Now I can be up in my bedroom looking out the window at my beautiful flower beds, and I want to water that one so they're both in this state. Then I change the state, then I change the state, then I change the state. And I can control 4 circuits with my 2 lines. This is what we call a decoder. A decoder, okay, this particular design scales such that you can make a decoder of any size. Obviously, we like sizes that are multiples, like powers of 2, right? Bless you. Given n inputs, we can control 2 to the n. A maximum of 2 to the n outputs can be controlled. Okay? In general, AND gates with various inverted inputs are ideal situations when there is a very specific input pattern required. Listen carefully. So this is an AND gate with, what, 8 inputs? AND gates where you are like hard coding the inverted inputs are a really great way to be like, look, there's only one combination of zeros and ones that will ever output 1. Because first of all, that's how AND works. AND only gives you an output 1 for one combination. But do you see here that the only way this would output 1 is if we see 0, 1, 0, 1, 0, 0, 1, 0. It'll only ever output 1. AND gates are phenomenal for that. Did I say that right? 0, 1, 0, 1, 0, 0, 1. Yeah, perfect. Cool. Isn't it also nice that it it's like the 0, right? Like it's a little circle for a 0, right? Yeah. And this is, decoders are so common that we have a fairly universal symbol for a decoder. All right? Decoders are a common tool used in digital circuits, and as such, they often represented with a single symbol. This trapezoid, that's a trapezoid, right? Or is that a rhombus? Trapezoid? Okay, there we go. All right? It's called the decoder. You can find these in digital. Under muxes, I think, components. Plexers, under plexers, a decoder. There it is, right? Let's zoom in real quick. Now, by default, number of selector bits. With one input, how many outputs can I have? 2. But I can change this to 2, and I can have 4. If I make this 3, how many will I have? 8, right? Perfect. Now, you might notice here that it only has one input, though. How can we possibly have, look, you just said there's 3 inputs. How could we possibly do that? Well, get ready for this. What we do is we use splitters and mergers. So, let's lower this real quick. Now, I showed you here in the picture, there's this little line here. Well, what you do is components, wires, we want splitter merger, okay? It looks like by default, this is a merger that wants to take 2 4-bit signals and combine it into one 8-bit signal. What we want is here we want 3 1-bit signals to produce one 3-bit signal. So we just go here and we say we want 1, 1, 1, and we want that to be 3. And then you would do that. So this is 0, and this now has 0, 1, and 2. Those are the 3 inputs, and then we can have 3 inputs control these things. Be mindful of the ordering. It should be obvious if you're paying attention, but it's easy to not pay attention and get your ordering backwards. But yeah. Pretty cool, I think. In fact, yeah, we're not going to be in time. Try to help me remember for Thursday, we will load up this circuit, and we'll play around with it a little bit just to make sure that it makes sense. Yeah, it's talking about signals. Any last questions before we wrap up for today? Cool. All right.